Hello students, welcome to today's session. So let us derive an expression for electric field due to electric dipole at equatorial point. So in the last class we have derived expression for electric field due to dipole at axial point, right? So today let us derive an expression for equatorial point. Okay, electric field due to dipole at equatorial point. So for that, of course, we require an electric dipole. So let us consider an electric dipole. Okay, so I'll take that as plus q here and minus q. Hope it is visible. Okay, so minus q separated by certain distance. So two equal and opposite charges separated by certain distance. So in general we take that distance as 2a, right? So separation between two charges generally taken as 2a. That means from the midpoint to one charge we can take that as a. So we can take this distance as a, and here to here again the distance is a. Now axial line. What do you mean by axial line? The straight line passing through that two charges, right? That is known as axial line. So now we require equatorial line. So a equatorial line is nothing but a straight line which is perpendicular to axis and which is passing through the midpoint of the dipole. Okay, that means if you take this midpoint as O, that equatorial axis that must be perpendicular to this axial line. That means it comes like this. Okay, and that must pass through that particular midpoint. Okay, so you can take this as equatorial axis or equatorial line. So on this line somewhere you have to take that particular point where you need to calculate electric field. Okay, so let us take that field here, that point here, somewhere here. Okay, and the distance from midpoint to that particular point, let us take that as r. So r is the distance of that particular point P where we need to calculate that electric field. Okay, so that point is at a distance r from the dipole or middle of the dipole. So this distance is a, right, and this distance is r. So at this particular point, due to this plus q and due to minus q, due to both the charges, there will be some electric field. Correct, no? So due to this plus q, there will be some electric field, and due to this minus q also, there will be some electric field. Therefore, the net electric field at P, that is what we need to we require to find out, right? So net electric field at P is nothing but field due to plus q and field due to minus q. So at any point, if you want to calculate electric field, what is our method? Yes, you have to keep a unit test charge or unit positive charge at that particular point. So the force experienced by that unit positive charge, that is nothing but electric field at that particular point, or electric field intensity. We call it as electric field intensity. So now what about this distance? We require this particular distance. The distance from plus q to this particular point. Just look at this. This is a and this is r. And if you look at this angle, this is 90 degree, right? So we can use Pythagoras theorem to calculate this distance. How? Yes, this is hypotenuse, right? So this square is nothing but a square plus r square. Correct, no? So a square plus r square, that gives this hypotenuse square, right? Therefore we need this distance, so you can take square root or to the power half. Therefore I'll write this distance as the distance from here to here in terms of a and r can be written as r square plus a square to the power half using Pythagoras theorem. Similarly, what about this distance? Distance of that point P from minus q. Again same, no? Why? Because this distance is a, this one is r. Therefore again this distance will be, using Pythagoras theorem, r square plus a square to the power half. Correct, no? So we got both the distances, right? Distance of point P from plus q and from minus q we got. Now what is our intention? We need to get an expression for electric field at P due to this complete dipole. That means you have to add field at P due to plus Q and field at P due to minus Q. Okay, so what is the method? Just place a unit positive charge at this particular point. Unit positive charge at that particular point. Now what happens? This one is plus and this one is plus. So there will be force of repulsion, right? Therefore, in which direction that force will be there? So repulsive force that will act along this direction or field at P. Okay, so okay, field at P due to this plus Q will act along this particular direction. So this is nothing but E plus Q. Okay, E plus Q. We can take it as E plus Q is acting along this particular direction, and repulsive force will also act along that particular direction. Okay, similarly, what about this E minus Q? This positive charge gets attracted towards this, right? Therefore, E minus Q will act along this particular direction. So E minus Q. Okay, why? If you look at this positive charge and this positive charge, which is greater? This one is greater. Therefore, the direction of electric field is always from greater charge to smaller charge here, right? So if you have similar charges, it should be from larger charge to smaller charge. Therefore, the electric field will be from Q to that unit positive charge. So it acts along this. But if you compare this unit positive charge and this negative charge, you know, the direction of electric field is from positive to negative. If you have similar opposite charges, it is from positive to negative, right? Therefore, so from here to here along this direction, you have to consider electric field. So E minus Q is acting along this particular direction. Hope it is clear, the direction of electric fields. Okay, so one is acting along this, one is acting along this. Now, if we consider these two fields, we require resultant of these two, right? So this is vector quantity. E plus Q is acting along this, E minus Q is acting along this. Therefore, two vectors are acting by making certain angle theta. Then what about resultant of that two vectors? There are two laws. One is triangle law and second one is parallelogram law, right? So out of that, you can take second one. If one vector is acting along this and one vector is acting along this, the resultant of that two vector can be considered as the diagonal of the parallelogram, right? The resultant is acting along the diagonal of the parallelogram. So this is the net electric field. Okay, so I'll write it here. Okay, this is the net electric field, that is E. Vector E is acting along this direction. So what do you mean by vector E? That is nothing but resultant of E plus Q and E minus Q. You can take this particular angle as theta. If this angle is theta, this should be theta. Okay, that should be theta. And if you just look at the direction, it is acting along this, right? The resultant of these two acting along the diagonal. That means if you just compare the direction of this electric field with the direction of dipole moment. What is the direction of dipole moment? Yes, it is always from negative to positive, right? Negative charge to positive charge. That means here the dipole moment is acting along this direction. Correct, no? Dipole moment, vector P, that is acting from minus to plus. But what about the direction of this? This net field is acting in a direction opposite to this dipole moment. Dipole moment is acting from right to left, but this one is acting from left to right. So if you just look at compare the direction with the direction of electric field with the direction of dipole moment, it is acting in opposite direction. Okay, yes. Now, whether complete E plus Q is acting along this? No. Similarly, whether complete E minus Q is acting along this? No. Only one component of E plus Q and one component of E minus Q is acting along this particular direction. You know how to resolve vectors, right? So if we consider E plus Q, just look at this. E plus Q is acting along this direction, right? So I will take that E plus Q here. So E plus Q, this is a vector. So you can resolve this into two components. one is along horizontal direction and one is along vertical direction. And if you consider this one as theta, if this angle is theta, in general, if you consider this angle as theta, then this will be adjacent side for this theta, right? Therefore, we can write this as E plus Q cos theta. If you have this vector as A, this will be A cos theta and this will be A sin theta. Therefore, this is A plus Q cos theta, sorry, E plus Q cos theta, and this is E plus Q sin theta. Now, which component is acting along this particular direction? E plus Q, its horizontal component or cos theta component is acting along that particular direction. Therefore, we can write this as E plus Q cos theta, that is acting along that direction. That is from E plus Q. Similarly, if you consider E minus Q, we can resolve E minus Q. Just look at this, E minus Q. Again, you can resolve this into two components. If you consider this as theta, just look at this. If you consider this as theta, then what happens? For theta, this one is adjacent side. So E minus Q cos theta we can write here, right? So this is opposite side, right? Therefore, if you can sin theta, if you consider, this will be E minus Q sin theta. Same for this. Therefore, this is E minus Q sin theta. I will write like this, E minus Q sin theta. Now, which component of E minus Q is acting along horizontal direction? That is E minus Q sin cos theta, E minus Q cos theta. Therefore, here we can write E minus Q cos theta. E minus Q cos theta is acting along that particular direction. That means the net electric field is due to two horizontal components, right? So, one is E plus Q cos theta and one is E minus Q cos theta. Both are acting in same direction. Therefore, if you want to get the resultant of that two, just you have to add them, right? Because both are acting in same direction. So if you add that two component, then you get the net electric field at that particular point P. Okay. So for that, the first requirement is we must write the expression for E plus Q and E minus Q. Okay, so let us write the expression for E plus Q first. So electric field, what is what I mean by E plus Q? E plus Q is nothing but electric field at point P due to that plus Q, right? Plus Q. So we can write E plus Q. Is it visible? Yeah. So E plus Q can be written as, what is the expression, general expression, electric field at a point? That is 1 by 4 pi epsilon naught Q by R square, right? So I will write that 1 by 4 pi epsilon naught as K. Okay, 1 by 4 pi epsilon naught is nothing but K into Q by the charge, that is Q divided by R square. R square means distance from here to here. That distance square. So what is that distance? That is R square plus A square to the power half. That one square. So what happens? The square root and square get cancelled. So you left with R square plus A square. Okay. So that is due to E plus Q. Electric field at P due to E plus Q. Similarly, we can write expression for E minus Q. I will write it here. So E minus Q, electric field at P due to minus Q. Whatever the charge, just magnitude of charge you have to consider. Therefore, that will be Q itself, right? Whatever the distance, but it is also same distance, right? Therefore, that one square means same expression you will get for E minus Q also. Therefore, R square plus A square. Correct now? Yeah. Now, net electric field, total electric field at P, that is due to that two horizontal components. So you have to add that two components. Therefore, E net. So I will write that as E equatorial. Okay. E equatorial, there is nothing but E plus Q cos theta plus E minus Q cos theta. Correct now? But if you write it in vector form, if you write here vector, so here you need to introduce dipole moment. As I said, what is the direction of dipole moment and net electric field? They are acting in opposite direction, right? Therefore, we can write this as minus p cap. What does that minus sign indicate? It indicates that the direction of electric field is in the direction, in a direction opposite to dipole moment. Now you may have one doubt. Sir, what about this E minus Q and E minus Q sine theta and E plus Q sine theta? What happens? Just look at this. The distances are same, right? Distance from plus Q to point P, distance from minus Q to point P. Distances are same. Similarly, what about the magnitude of charges? Plus Q minus Q both have same charge, Q. Magnitude of charge is also same. Therefore, at this particular point, if you just look at the direction of E minus Q and E plus Q, sine theta component, they have equal magnitude. Okay, these two have equal magnitude but acting in opposite direction. That means here E plus Q sine theta will act along this and E minus Q sine theta will act along this. They have equal magnitude and acting in opposite direction. Then what happens? Yes, of course, they cancel each other. These two components cancel each other. Therefore, net field at P is only due to that horizontal component or due to that cos theta component. So, no need to consider sin theta component because they cancel each other. Since they have equal magnitude and acting in opposite direction, they cancel with each other. Hope it is clear. Okay, now come to this. So, here E plus Q plus E minus Q into cos theta into minus p cap. Now what about cos theta? Just look at this. This is theta, right? Now if we consider this particular triangle, let us consider this particular triangle. Okay, so like this, I will rewrite that. Let it be theta. Okay, let it be theta, and this is r square plus a square to the power half, and this is r, and this one is a. Now here if you take cos theta, what do you get? Cos theta means adjacent side divided by hypotenuse, right? So adjacent side, for that adjacent side, for this triangle, for this particular triangle. Okay, so that is, I have written that here. Okay, so for that adjacent side is a. Therefore, we can write cos theta as a divided by hypotenuse, that is r square plus a square to the power half. And you know the expressions for E plus Q and E minus Q. Just substitute these two values. So what do you get if you substitute the values? K Q divided by r square plus a square plus K Q divided by r square plus a square, right? Into cos theta, that is a divided by r square plus a square to the power half into minus p cap. Now if you just look at these two terms, they are same, right? Therefore we can write that as 2 times. Therefore 2 times k q divided by r square plus a square into a divided by r square plus a square to the power half into minus p cap. Now just look at this, r square plus a square into r square plus a square to the power half. So if you simplify that, what you can write? You can rewrite that as, rub this. Okay. Okay, now this can be written as denominator r square plus a square to the power 1 into r square plus a square to the power half. That means r square plus a square to the power 3 by 2. Okay, in the denominator we can write it as r square plus a square to the power 3 by 2, and this I will write this as numerator as k into, okay, k into Q into 2A into minus P cap. Is it one and same? Just look at this, whether this equation and this one is same. Denominator to the power 3 by 2, right? And I will just rearrange this. Why? Because I want to introduce dipole moment here. Okay, Q into 2A, product of either charge and distance of separation between the dipole, that gives dipole moment, right? That gives dipole moment. Therefore, instead of this, we can write it as dipole moment. Okay, so here in the next one, in the next step, I'll write this as K into the dipole moment. Q into 2A can be written as dipole moment divided by R square plus A square to the power 3 by 2 into minus P cap. Now, if you consider this particular point far away from this dipole, that means compared to the length of the dipole, if that point lies at a point very far from this, that means if R is very much greater than A, okay, dipole is very small, but this point is considered at a large distance from that dipole, then in such case we can write this R square. That is similar to previous derivation. Okay, in the axial line also we did the same. Okay, so R square plus A square to the power 3 by 2 can be written as, that means here you are neglecting A. Substitute A equal to 0, that's all. Substitute A equal to 0. Then what do you get? R square to the power 3 by 2. That is nothing but R cube. Square and square root get cancelled. So in the denominator, instead of this, we can write it as R cube. Therefore, we can write E, that is equal to K vector P minus P cap, right, divided by R cube. Again here, this one sorry, this is not vector P, just magnitude P. Okay, magnitude P. So magnitude P into unit vector, that can be written as vector P, right? Just go through that previous derivation. Okay, so we can write this as vector P. Okay, actually this is the final expression, but one minus sign is there, right? So here you have one minus sign. Therefore, we can write this as, with that minus sign, we can write it as minus K vector P divided by R cube. What does that minus sign indicate? Minus sign indicates that the direction of electric field, net electric field at P is in a direction opposite to dipole moment, So if you substitute the value of K, then we can write this as 1 minus sign is very important. Okay, minus 1 by 4 pi epsilon naught P vector P divided by R cube. So this is the final expression for electric field at a equatorial point due to an electric dipole. That means electric field is inversely proportional to R cube, distance cube, and it acts in a direction opposite to the direction of dipole moment. Hope it is clear. Just go through this. It is very important. Okay, usually it is asked for 5 marks. Both questions. Okay, axial point and equatorial point. Field at axial point and equatorial point. Okay, hope it is clear. Just go through that. Yes.